Okay, our second speaker this afternoon will be Bhargav Bhatt. He will talk about the vanishing theorem.
Thank you. Thanks a lot for the invitation. It's a great honor to be speaking at this conference. The goal of my talk is to present a theorem on Noetherian rings, and I will eventually get to it. But I want to start off more on the geometric side. So I'm going to talk about some vanishing theorems in algebraic geometry, and then translate them to algebra, and then eventually tell you something about Noetherian rings. And please feel free to ask lots of questions. Okay, so let me begin with some classical vanishing theorems. So in this talk, I want to focus mostly on vanishing theorems in coherent cohomology. So cohomology of things like the structure sheaf, differential forms, line bundles, and so on. As we'll see, the methods involved in the sheaf theories, especially étale sheaf theory. But let's begin with the most kind of primitive example of what I had in mind. So let's say X over the complex numbers is a smooth projective variety. And I'm going to fix an ample line bundle on X. This is going to be and the most basic vanishing theorem in algebraic geometry that one learns about when one studies the subject is Serre's vanishing theorem. So, and I will just write it in a very simple special case to contrast it with later statements. And so it says the following. So there exists n sufficiently large, or let me write it this way. The cohomology in positive degrees of X with coefficients in the nth tensor power of L are 0, and is sufficiently large. There are lots of variants one can do. This is not really the sharpest statement. Also, the smoothness assumptions are not essential. In fact, I believe, although I didn't check, that if you look in this tax project, you'll probably find a version of this statement over any Noetherian base. Johan's nodding, so great. And so this is called Serre vanishing, and the reason I'm interested in vanishing theorems in this talk, and also just in general, is, well, they're kind of fun statements on their own right, but they're also useful in deducing geometric consequences. And so I wanted to explain this, at least for the first couple of the theorems I want to talk about. And so let me just explain the simple geometric consequence of Serre vanishing for people that have not seen this before, which might be the anti-set. I apologize. So let's say X is a curve, a Riemann surface. And little x is a point on X. So one of those sort of basic theorems in complex geometry is that if you look at the vector space of meromorphic functions on X, which have poles only at this point, and moreover you bound the size of the pole, then the resulting vector space is finite dimensional. And so it's reasonable to ask, what is the dimension of it? So let me write it in symbols. So the C dimension of the vector space of meromorphic functions F on C on X with poles of order at most n at the point little x. But at worst, excuse me, have poles of order n at x, and no other points. And so one can ask this question, as n varies, there's a naive expectation for what this number should be. Namely, if you're sort of imagining, if you're thinking locally, and z is a local coordinate that cuts out little x, then you expect that there's one more function allowed each time you allow one more pole, namely 1 over z to the n. And so the expectation would be that this grows linearly with n, and that's in fact true. So what what Serre vanishing can be used in conjunction with Riemann-Roch is to tell you that this number is equal to n plus some constant, which just depends on the geometry of the situation. And so in this very simple example, it confirms some geometric intuition you might have about what functions on Riemann surfaces look like. And the statement on its own has nothing to do with higher cohomology. It comes into the proof. Okay, great. So that's the first theorem I wanted to mention. This is, as I said, super general. It doesn't use the fact that I'm over the complex numbers. It doesn't even need smoothness. This is always true. The second theorem, however, is much more special to the situation we're in. So this is Kodaira's vanishing theorem. And these were actually from around the same time. If I look at the publication date, this was 55, and this was, I believe, 53. Although now when we learn the subject, this comes at a much more primitive point in the development. And so what this theorem says is it's about sort of the case not treated by this theorem. So this theorem is handling what happens with sufficiently positive twists of the line bundle. Kodaira deals with negative twists. And you actually get a much sharper statement. You don't get just an asymptotic statement, you get something on the nose. So what you get is that the cohomology in degrees below the top degree of X, the coefficients in L inverse. So just the first negative power suffices is 0. Okay, and this is really specific to the setup I'm in. As I'll talk later, it really needs the complex numbers. It also needs smoothness. Singularities cause problems here. And the form in which this theorem is often used is the dual form. So instead of formulating it as a statement about the cohomology of L inverse, one can use Serre duality to repackage it into the following. So Serre duality says you're supposed to change indices from I to d minus I, and then replace the sheaf with its inverse tensor with the canonical bundle of X. So omega X is the bundle of top differential forms on this variety. It's the determinant of the cotangent bundle. And you get a statement about positive degree cohomology groups of L tensor omega X. And this should be contrasted with the version of Serre vanishing that I didn't talk about, where I'm allowed to plug in arbitrary coherent sheaves over here. And the statement would be that if I give you a coherent sheaf, I can tensor it with L to the n for n sufficiently large to get a vanishing. And what this theorem is saying is that if you take the coherent sheaf to be the canonical bundle, just the first power suffices. And this is the theorem I want to sort of focus on in this talk. Let me give you at least one application of it, and let me stick to my planned board work. So here's a sort of sample use of sample geometric use of this result. So say you have a smooth hypersurface. Inside X. And so I'm imagining here, here's X, and here's this hypersurface H, and I'm imagining that L is giving me an embedding into projective space, and H is just a hyperplane section. So S is a section of the line bundle L. Okay, so in this context, what Kodaira vanishing lets you do is that it lets you produce geometric information on X, starting with geometric information on the hypersurface. So it lets you sort of go up in dimension. So the precise statement is that if you look at the global sections of the canonical bundle on X, twisted by a certain amount, L tensor 2, which are right additively. Then you can restrict such sections to sections on the hypersurface by taking residues of differential forms locally. And you get such a map. Well, you get a map at the level of sheaves, and then you can take global sections. And what Kodaira vanishing tells you is that this map is surjective. Okay, and so this is I'll explain why in a second, but let me just emphasize that this is very useful if you want to make inductive arguments let's say you're in some setup where you're trying to prove that the canonical bundle has a lot of sections. And you wanted some strategy that goes via induction on dimension. So you already solved the problem for your hypersurface. So you have lots of sections here, ignore the twists. Then this is saying it is surjective, so you can lift those sections. And so you suddenly find sections in one dimension higher, starting with sections on a hypersurface. This particular argument is used a lot in birational geometry. And I will come back to it. It will also be relevant later on in this talk. But again, I want to emphasize that it's a consequence about sections. That doesn't have much to do with higher cohomology. You're producing sections of the canonical bundle using a vanishing theorem. Okay, I guess I said I would tell you what the proof was, and the proof is very simple. Algebraic geometry is now in a state where you can prove a statement like this without really understanding what's going on. And so I'm just going to chase an exact sequence. Conclude. So the map of sheaves I have on the board over there, omega x going to omega h, it fits in a nice exact sequence. So you use the short exact sequence, which looks like so. So this is a short exact sequence which has been twisted up by L of a standard short exact sequence on differential forms. And if you chase this short exact sequence, you're trying to prove that a map from H naught here to H naught here is surjective. So it would suffice to know that the H1 of this sheaf is 0, which is exactly the H1 version of this theorem over here. So it's a very simple argument. Okay, great. Are there any questions? I was not supposed to. Sorry. You know, I was snickering when other people messed up board work earlier today. Okay. Right. So the question I really want to address in this talk is what happens to the Kodaira vanishing theorem if you're not over the complex numbers. But maybe before I get there, I want to tell you one ingredient of the proof of Kodaira vanishing, just to sort of point us in the correct direction. And so the key input to the proof, I mean, in one word, the answer is Hodge theory. And more precisely, what Hodge theory allows you to do is that it allows you to translate from cohomology groups of coherent sheaves, which are the objects showing up on the board, which are essentially objects in algebra. I mean, they have nothing to do with the analytic topology that can be defined over any field and computed purely algebraically. So what Hodge theory will let you do is it will allow you to convert these algebraic objects into topological objects. And on the topological side, you might have more tools at your disposal to solve the problem. So let me finish this. So Hodge theory translates this Kodaira vanishing theorem, which let me just abbreviate as KD, into a topological statement. And the topological statement that you get is the following. So you look at cohomology in degrees bigger than the dimension of a smooth affine variety. With complex coefficients. And what you want is that this group should vanish. And roughly, the idea is that this group has a Hodge decomposition, and this piece over here shows up as a summand in the Hodge decomposition. So if you know this group vanishes, you will know this group vanishes. And this is useful because this is actually a theorem, and it's a much older theorem. This is, depending on your training, either the Andreotti-Frankel theorem or Artin vanishing. It's a statement that any affine variety over the complex numbers of dimension D has the homotopy type of a CW complex of dimension D rather than of dimension 2D. And so since the dimension of the CW complex is dimension D, its cohomology in degrees D plus and bigger than D, it's obviously 0. And so you win. Okay, so this is very roughly what goes into the proof of this theorem, and we'll need versions of this later on in the talk. But let me now formulate this question that I want to address. What about Kodaira vanishing over other bases? And the two I have in mind are either fields of characteristic P. So let me just write FP. It could be any field of characteristic P, or even mixed characteristic. So, or Z localized at P, or so on. So this is the question I want to try and address in this talk. And let me first give you the easy answer to the question. So the easy answer is that there is a problem. And it's due to the fact that the theorem as stated is just false away from characteristic theorem. So I guess maybe let me say first something slightly positive and then say the negative result. So it's okay in small dimensions. Under some extra assumptions, which I don't want to get into, which have to do with liftability. This is the result of Deline and Luzi that I have in mind over here. So roughly, the statement you would get is it's in the setting of working over a field of characteristic P. If you have a smooth projective variety and an ample line bundle, and the data lifts to Z mod P squared, and the dimension of the variety is smaller than P, then you would have such a vanishing. That's what that theorem buys you. It would not necessarily say much in this setting. But in general, it's just false. KV fails. Examples were constructed by Mumford and then Raynaud. And actually, there's a whole literature on constructing counterexamples to Kodaira vanishing now, which is kind of fun to look at. But as far as this question is concerned, you might sort of regard this as an answer to the question and just move on. For my purposes, I want to go further because, as I said before, I'm not necessarily directly interested in the vanishing theorem itself. I want to know what about the geometric consequences you would get out of it. Are those still true in these more exotic settings? And it turns out that some of those can indeed be salvaged. So over here. So the idea for going forward, and I think this idea really came from commutative algebra in the 90s. So I will attribute it to Hoxter, Hunicke, and also Karen Smith. They were seriously sort of understanding the structure of Noetherian rings over characteristic P or a mixed characteristic. And the idea that emerged was that it's often profitable to work up to finite covers. And so what I mean is that maybe the statement of the theorem that you want is not true, but each time you encounter a bad homology class, a class that shouldn't be there, you could find a finite cover where the class becomes 0, and then maybe the geometric problem you're trying to solve can actually be solved because it can be solved after a finite cover. Roughly is the idea, and I'll try to make it more precise now. Any questions? Okay, so let's get into it. Let me talk about Kodaira vanishing. And I will straight away go to this setting, which is what I want to focus on in this talk. So the mixed characteristic setting. I will say something in passing about the characteristic P case. So Kodaira vanishing in mixed characteristic. And so let me fix a prime P. I guess I'm sort of doing that over there. And my geometric object that I'm going to work with will be a projective variety or projective scheme over the p-adic integers. So x over zp is a flat projective variety, and L is an ample line model. Okay, so the picture, which is similar to the picture I guess Elaine drew in her talk, is you're imagining X as living as being fibered over a curve. The curve is spec ZP in this case. And it has two interesting fibers. There's a characteristic 0 fiber, and then there's a characteristic P fiber. And we know the theorem over here. So let me call this XQP and XFP. We know our theorems on this fiber, and the obstruction comes from the theorems not being true on this fiber, and we want to understand it better. And so here's what we can prove in this context. So here's the theorem. So we want to prove a vanishing theorem up to finite colors, and the statement is going to be essentially exactly that. So, oh yeah, let me give a name to the relative dimension, maybe. Oh, let's see if we need it. So there exists a finite cover pi from y to x, which annihilates all the failures of Kodaira vanishing on x. So such that this pullback map pi upper star, which goes from the cohomology of x with coefficients in tensor powers of L. I'll try to write a statement that includes both positive, negative, and 0 tensor powers in one. So the pullback from the cohomology of x with coefficients in L to the k to that of y with coefficients in the pullback. If I restrict to torsion classes, which are the classes that are bad, because we already know this kinds of statements we want to know after inverting P. And so the statement is that this map is 0 for k being -1, 0, and 1. Okay, so k equals -1 is the version that corresponds to Kodaira vanishing. K equals 0 is an interesting statement about the structure sheaf, which I will talk about in a second.
So you assume x over ZP smooth?
No, we cannot assume x over ZP smooth.
But you don't have Kodaira vanishing characteristics.
Right, that's why I put torsion classes. So if x over ZP was smooth, the full group would be torsion. In k is negative, and I restrict below the dimension. But in general, you also get a version for singular varieties. Thank you. No, thank you for the question. Other questions while I try to figure out the boards?
What does cover mean?
Yeah, thanks for the question. So finite cover just means finite surjective map. There's no conditions on the ramification, and this is kind of essential. So I'll give an example in a moment where you see that you have the law arbitrarily ramified.
Are they reduced the schemes?
Sorry?
So x and y are reduced?
You can take them to be reduced because I'm only trying to prove something after passing to a finite cover. So the inclusion of the reduction of a scheme into a scheme would count as a finite cover. Yeah. Great, thanks. Other questions about the statement? Or yep.
Can you choose it to be separable?
Sorry?
Can you choose it to be separable when you're restricting to the characteristic P?
No, because already in characteristic P, you cannot choose it to be separable. Yeah, so thanks for the question. So, okay, let me just make some remarks. So, maybe the most important remark is, well, I think everything has come up in the questions. Let me write it. So, the analog of this theorem in characteristic P, an equal characteristic P, is not new. So this is from 2020. The analog in characteristic P is essentially where this idea came from. So and Smith. And I want to just explain what this analog says for H1 and K equals 0. So the structure sheet. So let me do it over here. So actually, I'll need more space. Let me go over here. So here's an example of what this theorem is saying. So let's say I not use little k because I used it over there. Capital K. Let's say capital K is an algebraically closed field with characteristic P. And X over K is a, let me just do the curve case, although the general case works exactly the same way. And then we want to, one group that this theorem is saying something about is H1 of the structure sheaf. And so what the theorem is saying is that you can find a finite cover of curves such that the induced map on H1 of the structure sheaf is the 0 map. And how do you do that? There are various ways. I mean, so maybe one thing I should have emphasized is this is the existence theorem. It's asserting the existence of certain finite covers. There's no uniqueness. So you can choose your own adventure. The way it works out for H1 is as follows. So it turns out that since I'm working in characteristic P, there's a Frobenius action on everything in sight. And so this finite dimensional K vector space decomposes into some V0 direct sum with some vector space which has a name, which is the étale homology of X with coefficients in Fp tensored up to my ground field. And the important features of this decomposition are that this is Frobenius nilpotent. So some power Frobenius acts as 0 on this vector space. And so now it's easy to imagine how this theorem is going to work. You're trying to annihilate this group by a finite cover. This vector space over here is annihilated by a finite power of Frobenius. So you just use the Frobenius. And this vector space over here comes from étale homology. Tautologically, elements of H1 with coefficients in Fp correspond to finite étale covers. And if you go up to those finite étale covers, those classes will die. So a combination of Frobeniuses and finite étale covers do the job in this particular example. Let me write. Use finite étale covers plus Frobenius. And so this is also, I think, so if you take X to be a supersingular elliptic curve, the entire contribution comes from this factor. And one can prove that finite étale covers do not kill that curve. You really need to involve the Frobenius. So some kind of inseparability is forced on you. Okay, great. Other questions? What am I supposed to do here? Yes, that was the first part. Okay. Right, so that was the first remark, indicating how this theorem works in characteristic P just for H1, and also showing that ramification is kind of essential. Maybe the second remark I want to make is, so maybe this is already clear from the example, but that theorem up there is saying something for k equals 0 and 1, whereas the Kodaira vanishing theorem was only a statement about k equals -1. It was the negative powers of the ample line model. So the fact that you can say something about positive or non-negative powers of L is really some arithmetic phenomenon, which is hopefully also clear with this example. we involve the Frobenius. It doesn't have any counterpart in characteristic 0. So maybe a fun exercise is to try to prove the k equals 1 case of that theorem in characteristic P, just by observing how Frobenius acts on line bundles. Okay, so that was theorem A. It's this version of Kodaira vanishing and mixed characteristic that is actually true. And as I said, I was interested more in some applications of this theorem rather than the particular vanishing. And so one application that we were able to carry out soon after this theorem was proven was the following. One application. This is joint work with a lot of people, so I'm going to use acronyms P, M, P, S, T, W, W, and TY. Okay, so Lin Chuan Ma, Joel Patakali, Carl Schweid, Kevin Tucker, Joe Waldron, and Jakub Wittejek, who's there, and Takamatsu and Yoshikawa. And essentially, what this is saying is you can do parts of the minimal model program in mixed characteristic in small dimensions. So one can run the MMP over, not quite over Z, because some small primes cause problems, but you need to invert 2, 3, and 5. So 30. Right? No, I didn't mean the 30 part. I was checking about the primes. Okay. And I don't want to talk about any more about the application. I just want to say that the way this theorem A becomes relevant over here is exactly by this lifting argument I alluded to earlier.
Means 3 degrees.
Sorry?
Means 3 degrees.
For threefolds. Thank you. You can run the MMP over ZHN 30 for threefolds, arithmetic threefolds. No, otherwise I would have talked about that here. Right, so the three-dimensional restriction comes from many sources. But one of the main ones is the lack of resolution of singularities beyond dimension 3. Yeah.
Sorry, in the statement of theorem A, could you clarify which degrees we're countenancing?
Which degrees
of cohomology are we talking about?
Okay, so that's a good question. Something I was trying to not get into, but I believe it's correct the way it's written from all cohomology degrees because of the way torsion works.
So even for k equals -1, it's like a stronger statement than our vanishing.
I mean, on the face, yes, but not really if you look at how it works. I mean, somehow if you look at the top dimension cohomology group, so first of all, the relative dimension of x over ZP is the total dimension of x minus 1, and that's the relevant quantity. And in that top degree, if you look at the torsion classes that show up via Bockstein homomorphism, they really come from classes in 1 degree lower. And so you can then, as long as you know the theorem in 1 degree lower, it's good enough. But yeah, in mixed characteristic, you get this kind of funny phenomenon that it's actually a statement in all degrees.
When you say arithmetic threefolds, are you talking about relative dimension 2 or relative dimension 3?
Two.
Relative, okay.
Yeah.
Okay.
Okay, great. Other questions? So what I want to do now is go to algebra. And so one of the motivations for this theorem A really came from the problem in commutative algebra I'd wanted to solve for a long time. And so there's a version of this theorem in the local algebra setting as well. And I would like to talk about that version now. This is local vanishing. And I like drawing a picture to motivate local Kodaira vanishing from global Kodaira vanishing. Maybe this audience doesn't need that picture, but I will draw it anyways. So essentially, there's a dictionary to relate. Whenever you have a projective variety, you can construct a certain singularity, which is the cone over the projective variety. And there's a correspondence between the geometry of the variety and geometry of the singularity. And it goes as follows. So let me recall. If you have a projective variety, or maybe I should say projectivized variety, it's really sitting inside projective space. You can draw the following picture. So here's X, you can contemplate the total space of a certain line bundle over X, which is O of -1. This is the one I want to use. And O of -1, well, since it's a line bundle, it has the zero section. And the choice of -1 allows me to contract the zero section algebraically. So what I get is a singular variety where I've contracted exactly the zero section, but nothing else. And this is nothing other than the cone over X. So the affine cone over X in Pn, which sits inside An plus 1. And the basic principle is that projective geometry of X is encoded in sort of the local geometry around the singularity. In particular, things like coherent cohomology on X correspond to some local cohomological invariance at the singularity. And so given a statement like theorem A, you might wonder if it translates, first of all, to some statement on the cone. And then if it does, you might get lucky and the theorem might be true for arbitrary singularities, which are not necessarily cones. So it's just a statement about commutative rings, and that's what happens here. Talk about that. So the local algebra version of theorem A is theorem B. I'll state it as follows. So let's say R, comma M is a Noetherian local domain, which is nice. So I need to assume it's excellent. If you don't know what this is, please ignore it. You will not lose anything. And it needs to be in mixed characteristic, which in this algebraic language means that P is in the maximal ideal. So R mod M is a field of characteristic P. Okay, so I'm imagining this R is really the local ring at the singularity. And sorry?
P is not zero.
Oh yeah, P was a fixed prime throughout my talk.
Yeah, but it's in the ring.
In R.
Oh, that's allowed. Sorry, characteristic P rings are allowed, if that's the question. Yeah, thank you. Right. Although the theorem is going to be known in that. So R plus is the integral closure of R in an algebraic closure of abstraction field. Okay, so this is some huge object. Going against the spirit of the conference, it's not Noetherian. It's really some kind of a bookkeeping device for keeping track of all possible finite extensions of my ring in one object. R plus, and the theorem is a theorem about R plus, and it's the following statement. So R plus mod P is Cohen-Macaulay. Cohen-Macaulay is R module, just Cohen-Macaulay. And so let me try and state this in slightly more down to earth terms. Is there a question?
I was wondering, I thought R plus was going.
R plus is,
Okay, R plus mod P is going Macaulay, but not R plus.
okay, so thank you, that's a good question. So you can ask this question in characteristic zero. So if R was a ring of characteristic zero, and then R plus is never Cohen-Macaulay as soon as the dimension is at least 3. Essentially, R plus keeps track of all possible finite covers of the fixed Noetherians of like affine space. So as soon as you see one non-Cohen-Macaulay singularity in characteristic zero, you're not going to be able to kill it further in characteristic zero by going up along finite covers. So starting with dimension 3, this statement would be false in characteristic zero. So you cannot expect R plus on the nose to be Cohen-Macaulay, because if it were, then after inverting P would be Cohen-Macaulay, which is contrary to what I was just saying. So this is the simplest statement you can make. You can also formulate it as saying that the p-adic completion of R plus is Cohen-Macaulay on the nodes. That turns out to be equivalent.
What does Cohen-Macaulay mean in the non-Noetherian case?
Yeah, thank you. So what I mean is in terms of okay, one formulation I could give is in terms of local cohomology. So since I'm working with a local ring, I just mean the local cohomology of R plus mod P at the maximal ideal vanishes until the maximal degree. There is a concrete version, which in terms of regular sequences, which I was about to write down. So concretely, what the theorem is really saying is the following. So if R is a ring of mixed character state, which comes equipped with a Noether normalization, I guess another theorem of Noether. So if you have a complete Noetherian local domain, you can always essentially find nice Noether normalizations like this. So it can realize it as a finite extension of a ring of formal power series. So if R containing ZT adjoint x1 through xn is a finite extension, so then something good happens. So let me first say in words what's going to happen. So in this ring ZT adjoint x1 through xn, the xi's are very independent from each other. They have no relations between them, and technically speaking, what I'm saying is that they're form a regular sequence. There are no bad relations. But R is just a random ring, which is finite over something like this. It could have tons of bad relations. It, for example, does not Cohen-Macaulay. And what the theorem says is that whenever you encounter such a bad relation, it should not survive the passage of going all the way up to R plus, and you actually get a more finitistic statement. So then there exists a finite extension, a further finite extension, R to S, such that any bad relation you see on R becomes trivial on S. So any bad relation on the xi's in R mod P is trivial in S mod P. And okay, you might say this is not super concrete because I didn't actually tell you what bad relations means. For example, you could formulate this in terms of a certain Koszul homology group. Whenever you have a sequence of elements of a ring, you can write down the Koszul complex on that sequence, and the homology of that complex measures the failure of the sequence of elements to be a regular sequence. And what this is saying is that the induced map on Koszul homology when you go from R mod P to S mod P is the zero map. And so this very special case of this theorem, which is already new, is the case n equals 2. So you only have two variables, let's say x and y. And in that case, what this is saying is that if you have a relation of the form ax equals by in R mod P, then it's not going to be the case that y divides a and x divides b in R, but it will after you go up to a finite extension. Okay, great. How am I doing? Okay.
And so is that really what it means, or just ax equals by becomes divisible there? I mean, there can be new bad relations coming.
Absolutely. So yeah, thank you for the question. Right. I'm not saying S is going to have nice properties. It's only that the ones which were bad over here become good over there, but there will be new bad ones. And this is related to the discussion with Elaine, because sort of in characteristic 0, you're not improving the situation. And so there will be non-Cohen-Macaulayness which survives. It's just mod P becomes 0 and the transition maps become 0. Thanks. Other questions? Okay, so the theorem, theorem B was motivated by some questions in commutative algebra I was interested in, and it leads to the solution. I don't want to talk too much about those applications here, but maybe I will just mention one of them, which I think is easy to appreciate, which is the following. So this theorem B implies something which is called the direct summand conjecture. which was not proven this way. So the following theorem of Andre is a major open question in commutative algebra for about 50 years. And then Andre solved it in 2016 using perfectoid geometry in a crucial way. But the theorem is completely elementary once you know what regular rings are. So it states the following. So R is a regular ring. And actually, let me even say it in an even more special case, which is equivalent to the general case. So let's say R is Z adjoint x1 through xn. Polynomial rings in n variables over Z. And R to S is a finite extension. So it's a finite injective map of rings. In this case, the theorem says that there's a R linear section backwards. There exists an R linear splitting, R linear section to I. So in the world of modules, you can split off a copy of R from the ring S. That's the statement, and as far as we know, there's no sort of elementary proof of this. Andre's proof is fairly involved, and so is the proof I'm about to tell you about, as we'll see in a second. But at least it's very easy, I believe, to understand why this theorem should be related to some theorem like this. Namely, in theorem B, if you assume that this ring is also regular, like the polynomial ring is, then this Cohen-Macaulay-ness is equivalent to flatness over a regular ring. There's something called the miracle flatness lemma in Brian. And so this miracle flatness lemma will tell you that R plus is flat. And if you complete the situation, so if you work or power series rings, then flatness implies freeness. And so in that setup, you have visibly demonstrated something bigger than S, which is a bunch of copies of R as a module, and then you just pick off a suitable summand from that big module to find your R linear section. So there's a relatively easy way to go from theorem B to the direct summand projection. The statements are not equivalent, but at least that's one application of this theorem that I could tell you about in a few minutes. Okay, great. Any questions? Yeah.
What's the reason for taking the algebraic closure of frac of R when you define R plus?
So I want to be able to talk about all possible finite covers, because the theorem that, like, this is supposed to be a local version of theorem A, and theorem A is saying that something good happens after you go to a finite cover, but you don't know what that finite cover is. And so the way we're going to prove this theorem is by thinking about the inverse limit of all possible finite covers. And that's what R plus accomplishes. Other questions? Okay, so in my remaining time, I want to talk about very briefly about the proof, what goes into it. So, there are two essential ingredients I want to highlight, and I will spend most of my time on the first one. And so this is the Riemann-Hilbert correspondence, or some version of it. So I shouldn't say correspondence because we only have functors, Riemann-Hilbert functors. And so this is all joint work with Jacob Lurie. And maybe I should say why this is a reasonable ingredient. So when I talked about Kodaira vanishing incharacteristic zero at the start of the talk, I tried to emphasize that the sort of key input in the proof is Hodge theory, where you translate the algebra statement to a topological one, and then you have more tools available. We want to do the same thing in this mixed characteristic situation. And the topology now has to involve sort of mod p coefficients rather than complex coefficients. So we cannot use Hodge theory or classical Hodge theory. Instead, we can try to use p-adic Hodge theory. And that's what these Riemann-Hilbert functors are about. And so the version I need is the following. So I left the relevant notes in the back over there. Oops. Okay, so let's see if I can do this. So let's say R over ZP is a smooth algebra. The Riemann-Hilbert story is a geometric story. So I don't want to worry about complications that come from the arithmetic of the p-adic integers. I want to pass to the algebraic closure. And so I really want to talk about, well, let me call this ring R0, the one that's defined over ZP. And then I will call R its base change to ZP bar. Or ZP bar is the integral closure of ZP in QP bar. I guess another name for it would be ZP plus. So this is also a smooth algebra. And the picture is exactly the same as we had before, but maybe I'll draw it because it'll be more useful now. So we draw the picture. So here's a picture of stack R. Let me spec ZP bar. Again, it has 2 points, and we're going to play some game that involves going from one fiber to the other. So let me use, I guess, red and blue. Red is the fiber we can't understand, blue is the fiber we can understand. So that's the Kirchig key fiber, and this is the Kirchig 0 fiber. Okay, so this one is, so let me call it spec R X. This guy over here is X over QP bar, and this guy over here is X over FP. Okay, so why am I doing this? The Riemann-Hilbert story is going to be a dictionary to relate the topology of what's happening on the blue fiber, with the algebra of what's happening on the red fiber. So more precisely, there's a functor. There exists a natural functor called RH. And this functor is going to go from the constructible FT sheaves on the characteristic 0 fiber. So roughly the topology of the generic fiber, two quasi-coherent sheaves on the special fiber, or more precisely, R mod P modules. And it has a lot of good properties. I'll emphasize some of them, but maybe already let me emphasize I'm being sloppy here. Really, I should be working with the constructible derived category over here and the derived category of R mod P modules over here. But I'm just trying to convey a flavor of what's going on. You're going from topology on XQP bar to algebra on the special fiber. Okay, and so what does this functor do for you? So it has many nice properties, and the two I want to emphasize are the following. So satisfying. The first one is it interacts well with T structures. So in the classical Riemann-Hilbert correspondence over the complex numbers between D modules and constructible sheaves, if you're interested in honest D modules on the D module side, then the object you want to use on the constructible side is perverse sheaves. And the perverse T structure matches up with the standard T structure on the D module side. And something similar happens over here. Perverse sheaves are the ones which have good properties. And the specific one I want to emphasize is the following. So RH of the perverse FP sheaf so this is now an object in commutative algebra. It's an R mod P complex. And the statement is that this is an almost Cohen-Macaulay complex. So ignore the word almost. This is saying that this complex has the kinds of commutative algebra properties that I want in the main pair. The precise statement, the way Cohen-Macaulayness is defined is exactly through local cohomology, as I was alluding to earlier. And this almost over here is in a technical sense, which I will not get into from the Snickers, I know that some people know about it. Great. And okay, so why is this useful for us? It's useful because in my theorem, which is still there, I'm trying to prove something is Cohen-Macaulay. And this is giving me a recipe for finding a bunch of Cohen-Macaulay complexes. And so the best case scenario would be that the thing I'm interested in is RH of the Burr sheaf. And that's what happens. So R plus mod P turns out to be equal to RH of some M, where this is a perverse sheaf. And so if you just blindly combine A and B, you immediately get the almost version of the theorem. So therefore, A plus P implies that R plus mod P is almost Cohen-Macaulay. Okay, and so now maybe I owe you one word about what almost means and why this is not the end of the story. So almost here is in the sense of almost mathematics a la all things. And practically what that means is, for example, over here, you're trying to prove that some module is Cohen-Macaulay. Being Cohen-Macaulay means that certain cohomology groups vanish, these local cohomology groups. And what being almost Cohen-Macaulay means is that those cohomology groups don't quite vanish, but they're very small. Namely, they're killed by arbitrarily small powers of P. So not only are they P torsion, but they're killed by, P square root of P, or the P root of P, or the P to the nth root of P, all of them. And so there's some sense in which they're very small, and what Fernholz calls them is they're almost zero. And so if you work modulo almost zero modules, then this is saying that R plus mod P is Cohen-Macaulay. And so there's still a problem, like this is not the end because you're not actually proving Cohen-Macaulayness, but this is taking you a big chunk of the way there. And so the second ingredient of the proof is what comes in when you try to come back to the real world. So you have proven an almost statement, and then you want to deduce an honest consequence out of it. And it takes a lot of hard work. It's about 50 pages, so I definitely don't want to explain it here. But very roughly, we use prismatic cohomology. To turn an almost vanishing into an honest vanishing. And I will just say one sentence on why prismatic cohomology is relevant. Namely, prismatic cohomology is a cohomology theory for objects in mixed characteristic. And one of the features that's essentially a design feature of the theory is that it comes equipped with a Frobenius action. So the output of prismatic cohomology is something which has a Frobenius action. And what this Frobenius action practically allows you to do is it allows you to mimic certain arguments that we did earlier in characteristic P using the Frobenius, but now in this mixed characteristic setting where you don't have Frobenius. So I think that's all I wanted to say about the proof of theorem B. And I have, I think, 1 minute left. And so I wanted to mention one lemma that goes into the first part of the proof, which I think is just kind of fun. And I really enjoyed it, which is the following. So I guess the lemma is going to be an answer to the question of what M is. So I didn't say where this perverse P sheaf came from, I just told you it exists. And so the lemma is saying what this M is, and it's the following statement. It's a statement just about algebraic varieties over the complex numbers. So let's say X over C is an algebraic variety. Pi is going to be the geometric version of the absolute integral closure. So you do the commutative algebra construction with R plus at the level of affines and then glue. So it's an inverse limit of all possible finite covers of X. And then the conclusion is that in this situation, if you look at the push forward of the constant sheaf, Fp, shifted by the correct amount, so shifted by the dimension. And then this is actually perverse. This is not that hard to prove, but once you make this observation, it's not so hard to go from that lemma to this to point B on this side. And so then the general machinery of this Riemann-Hilbert correspondence will at least almost prove the theorem for you. Okay, I think that's all I want to say. Thank you.
And Kodaira vanishing, we don't know.
Kodaira vanishing.
Yeah, you don't know.
I didn't explain Kodaira vanishing. So the proof follows a similar strategy. Okay, this is not quite an accurate summary of the proof, but essentially you do this proof GM equivariantly on the cone. That's roughly what you do. I mean, there are many more complications that come up along the way. You need this sort of a counterpart to this lemma involving the geometry of, like imagine you have an ample line bundle on X and you pull it back to X plus. You need certain perversity statements for this sheaf over there, but very roughly what you do is you do the GM equivariant version of this proof. I'm happy to explain more later, but it'll take too long.
So if knowledge, check about.